how do we use calculus to find the center of mass? Well, we don't directly find the center of mass. We find these things called the moments with respect to the x and the y-axis. Okay, moments are these weird abstract topics or ideas that you really can't give that much context to. You can have different moments. You can have moments of force, moments of inertia. But for our purposes, you really just need to be okay with the fact that a moment is a mass times a distance. Okay, so a moment of an object with respect to some axis, it's just the mass of the object times how far away from that axis the object is. Okay, I know it's a little vague, but you have to deal with it. So the overall approach of finding the center of mass is we're going to take our region, we're going to divide it into little cross sections, surprise there, and then we're going to find the cross section's moment or moments, x moments and y moments, and add them all up. So we get a total moment for the object for x and y. And then we're going to use the moments to figure out the x and the y coordinate of our center of mass. Okay? So how do we actually find the moments? Because that's the only hard part. Our moments, for example, let's do my first. Moment with respect to the y-axis is going to be, again, mass times distance. So it's going to be the mass of each cross-section times how far away from the y-axis it is. Okay? Here is the little hiccup. How far away from the y-axis, my, is going to be your x-coordinate. Okay? So inside our moment for y, we're going to have an x in there. Okay? That's sometimes it throws people off, but it's not. You really don't have to memorize. You can understand the fact that, look, that x is in there because we're saying each cross-section is some units away from the y-axis, but that distance is going to be dependent on the x-coordinate of the cross-section, not its y-coordinate. Okay? So that's why that x is in there. And again, x times some mass. This whole thing is just your mass of each cross-section, though, I should add. So, you know, if you're sort of wondering about that, you should probably look up masses and densities and stuff like that. But so that's your mass, and the x bar is the center of mass, the x center of mass of your cross section. Now we can just reduce that to x because our cross sections, remember, are so thin that their x center of mass is basically the same thing as their x starting point. Okay, and that's why we can get rid of the bar over there. And our rho is for APMA 1110. Our rho is going to be constant. So it's not a function, and our so basically m is rho times a. Now rho is rho. What is a? A is the area of your cross section, which is just a rectangle, dx times the height. The height is just the function because that's how far above the x-axis it is, right? So again, the rho, and then your area is just dx, this little width, times your height, and that gives you your area. Okay, so then pull the rho out, and you end up with a pretty easy integral to do for my. For mx, you do something very similar, except here it's distance away from the x-axis. That's going to be the y coordinate of the center of mass of each individual shell and each individual cross section. So for example, for this one, it's going to be over here. For this one, it's going to be over here. Okay? So all we do is say, well, it's the y center of mass of my cross section times the mass. The mass business is the same as here, but the y center of mass of my cross section is just going to be the height of my cross section divided by 2. That's it. Okay? So then we get the fx squared and a rho out and 2 on the denominator. So then we find x bar and y bar. There's another hiccup. We again switched them. It's not mx over m, my over m. It's my over n over m. And you can think of this as switching back this initial switch that we did, even though that's not the actual reason. The actual reason is through the dynamics of, if you think about it, again, the moment is just a distance times a mass. So we're taking the mass away from the moment in y, and it gives us back the how far away from the y-axis our actual center of mass is. Okay? So that's a little abstract, But let's go ahead and do another abstract version of this, except this one is going to be a little tougher, okay? So over here we have two functions. Now we don't have the luxury of just being bounded below by the x-axis. Now we have another function bounding us from below. So let's go ahead and do it. Our my is going to be the integral of the x center of mass, the x bar of each cross section, times our mass, right? So integral of x bar rho dA, which is the same thing as the integral of, what's x bar? Well, it's just x, right? If I draw my cross sections, a couple of them, I'm going to be, wow, I'm going to be x units away from the y-axis, so it's just x, and my rho dA, my rho is just rho, dA is going to be f of x times dx, right? So it's just rho x f of x dx. My mx should be something similar. It's just going to be integral of y bar rho dA, which is equal to the integral of, now here what I'm interested in is the y center of mass of each cross section, bounded above by this and bounded below by this, okay? Now if you remember how we do, for example, if I have an object at 3 and an object at 5, center of mass of that thing is going to be 3 plus 5 divided by 2, right? Or the midpoint, if you remember from geometry. It's the same idea. So here we're going to have f of x plus g of x divided by 2. And that's our center of mass of each, the y center of mass of each cross section. Then the rho is just the rho. I'm going to actually pull it out. And then our dA is going to be dx times our height. Now what is our height? Well, it's just that thing minus that thing. Bounded above minus bounded below. Done. It's going to be f of x minus g of x. Okay? So now what I can do is clean this up a little by recognizing that this is difference of two squares. And there you go. Okay? So that's going to be our expression for mx. Now for x bar and y bar are going to be, remember, again we switch them, my over m and mx over m. Okay? And what is m? Just to be clear, m is just going to be rho f of x, rho dA, which is rho times f of x dx. Okay? So there you have it. It's not terribly hard. It may get a little more involved, but I try to do something that's abstract so you can see how sort of the dynamics of the whole thing work without actually using an example. So the things that you need to watch out for are the switches. There's two of them, one where you're calculating my and one when you're calculating, not my, but the moment, and the other one when you're calculating the center of mass. So you switch them twice, okay? And besides that, there are no really quirks to this whole methodology. So there you have it.